Here's another score from a recent hamfest. This one cost me 45. It's a Yaesu YC-355D frequency counter. It's only 5 digits, so nothing special in that regard, but they are Nixies, so that's why I got it. We've got power switch. There's 2 ranges, kilohertz and megahertz, and what's that about? I've forgotten what that's about. Up to 35 megahertz or up to 200 megahertz. In that case, the input signal goes through a pre-scaler. Not sure what that's about. Anyway, on the back, came with a power cord, an IEC power cord, but a useful right angle one. Notable about this thing is it can also run off 12 volts DC. There's a switch there to select it. Internal, external reference. I don't remember seeing that in the circuit. The manual for this is pretty easily available. There's only one copy, but it's in lots of places. Apparently quite popular with ham radio enthusiasts. So before turning it on, and it comes with a little bail, I'm not sure what these screws on the side are for. Is that how you open it? I guess it is. Yeah, before turning it on I want to have a look inside, so we'll do that, eh? And my new camera mount arrived to replace my homemade wooden jobby, and maybe doing this thing up too tight is what caused my lens error, squeezing the lens too tight, stopping the lens being able to zoom in and out, and then I can use my proper tripod instead of this little thing. Anyway, back to the video. Yeah, it looks like just undoing these makes the covers free. So, lift this off, and it's a bit dusty, a little dirty. Yeah, so just a lot of 7400 series ICs. There's the time-based crystal, which apparently is pretty well spec'd. The manual says do not replace with another sort. You've got to use that one from Yaesu. And looks like, oh, that's the pre-scaler, I think, yes. Yeah, this chip here, it's got a little heatsink on it. MS-3380, I think it was. Can't find any information on that. So, I wonder how good these caps are. It's probably sort of safe to turn on. I'll power it through a current limiter. Does the bottom come off? Yeah, the bottom comes off as well. More stuff down there. And the Nixies are hidden behind that bit of cardboard fish paper, and there's a neon overrange indicator there. Alright, I'll set up a dummy load, a current limiter, and power it on. Okay, there it is. I've got this 75 watt light bulb in series with the incoming mains, and we should be looking for about 18 watts according to the manual. So let's turn on the power there, and here. Oh, Nixies are on 13.4. okay, looks like we can bypass this. Reasonable, 13.14 watts roughly. So, and 0 count, and nice Nixies. Beautiful. This moves, no, yeah, that moves the decimal point. Does this? These switches feel a bit dicky, so probably some deoxit wouldn't go astray there. That looks pretty nice. Let's stick a signal in it and see what it says. Right, I'm just checking there. I've got 1 volt peak to peak, 1 kilohertz signal. I'm checking that because when I first tried it, this thing wouldn't work, and it still won't, because I had it on external trigger time base. Let's switch it to internal. Is that any better? Not really. Changing the frequency, doing nothing. Oh, 1. Okay. Crank this up. Oh, it is working. It is working. Yeah. 7 kilohertz. 7 kilohertz. not working in the kilohertz position. So we've got 9 kilohertz, which is 0.009 megahertz. Crank it up. There's something wrong, and this switch is a bit dicky. Alright, I'll go up to megahertz now. Right, this should be megahertz. Yep, 1 megahertz. 10 megahertz. That's looking pretty good. Just seems to be a dicky switch there. And yeah, we've gone past what it can cope with on the low range, so let's go back to 35 is okay, 36 megahertz, 37, 38, 39, yeah, 40 megahertz it starts to lose the plot. Switch in the prescaler, 40 megahertz, 41, 60 megahertz. Yeah, I think that's the limit on this thing. Yeah, it seems to work. The only thing wrong is this switch. I wonder if I can clean that up and get a better result. Try that. I've just given it a clean with some CRC, see if that helps. Right, without the dummy load and the oscilloscope now, on the megahertz range, 1, 2, 3, 4, that's doing what it should. 0.006 megahertz is 6 kilohertz, but if I go to the kilohertz range, 6.027, that sort of looks right. And okay, how good is this? Probably not very, so we expect a bit of variation. We go to 7, and this had me tricked for a while. You've got to wait a second for it to update, and possibly 2 seconds, because you're halfway through one update, so it's wrong, and you've got to wait for a complete second of the new frequency. So 7's looking good. This should be 8, 9, so it's wrong while we're changing, but then we've had a full second of, and we get 10 kilohertz. Alright, so I'll just whack it up a bunch. Let's go to 35 kilohertz. There we go. That's not looking too bad. 53 kilohertz. That 3 looks a bit weak, doesn't it? The 3 on that digit there. 52, 53. Yes, I'm getting 0 sometimes. 88 kilohertz. That's spot on, isn't it? Go check out the outer range. Whoops. 99 kilohertz. One more. We could get over range. There's 100 kilohertz coming in. That should be coming on. 101. Occasionally popping on. 102. And maybe only flashes once per count. 100 kilohertz, and it's not flashing at all now. Should be coming on. 99. And let's fiddle with lower digits. Down in the 1, so 99 kilohertz and 1. There we go. 99001, 99001. 2. 3, 4, 5. 4, bit of a disagreement there. 4 and 5. 5 and 5, 6 and 7, 99 and 10. That's pretty good. I just get the feeling everything there's a bit grubby, dirty, needs cleaning. Everything's got this sort of film of dirt. Yeah, I'm not sure how good these capacitors are here. Those electrolytics probably a bit sad by this stage. And you can see that modification. Some trace has been cut across there, and looks like some RG316 to the switch at the back, and it says extra. I presume they mean you don't put a crystal in there, you put a frequency. Yeah, they're not replacing the crystal, so yeah, that's an external signal input, 1 megahertz I presume, and it's supposed to have maybe this here may, according to the manual, I think there's a 1 megahertz output from that clock, and it looks like maybe it's been repurposed as the external input now. And I don't know if it's visible, as well as this what appears to be dirt. It might be a bit of corrosion. You see speckles everywhere. On these polycaps there seems to be some sort of smoo / fungus. You know, tiny little white dots, and I hope you can see that. Yeah, don't like the look of that, so I think I'll give this whole thing a wash in isopropanol and find replacements for all these electrodes. That one even looks like it might be a little bit bulging, and more smooth there on that ceramic. Yeah, so replace the electrodes, check that the 5 volts is correct. There's an adjustment for that there. The crystal seems to be pretty spot on, so I won't touch this trim cap unless I manage to drift it. And I was also inspired by a video on the signal path, which led me to think of an interesting mod for this thing. It'll only work on the kilohertz range, but it might be worth doing, and I think I found a way of doing it that doesn't involve any permanent alterations to this, just soldering a few wires in here. The only permanent alteration would be drilling a hole for a pot on the back panel, but if I get around to that and if it works, I'll do a video on it. So yeah, that's pretty much for looking at this thing physically. So let's have a look at the circuit for this thing, because it's got quite a nice feature to do with this DC operation. So turning to the theory of operation, there's the block diagram. Now this frequency counter, like all others, works by counting the number of cycles occurring on the input signal in a accurately known time period. In the case of this thing, that time period is either 1 second or 1 millisecond, and that time is given by this gate pulse here. That's active for either a second or a millisecond. Now the input signal can go directly into the input amplifier, or when we switch it to the high frequency range, it goes through a prescaler which divides it by 10, must need some buffering after that, and into the input amplifier as per normal. That goes through a Schmitt trigger which cleans it up into a nice square wave, ready to go through the input gate if the gate pulse allows it. When it does, it goes into these decade counters. They're 4-bit decade counters, so rather than counting to from 0 to 15 like a binary counter does, they only count up to 10 or 9. When they get to 10, they reset themselves and produce a pulse that goes out to the next one. So he counts to 9. When he gets to 9, he resets to 0, and this one gets a pulse and counts a 1, and so on, until we get to 99,999. One more pulse and it overflows out here, which turns on the overflow indicator. Now at the end of the gate pulse, we want to know what we counted up to, and that causes this signal up here to strobe the value in the counters into these 4-bit latches. This signal clears the latches and they start counting again with a new gate pulse. So this holds the previous count while the counters are busy counting the next sample. The count latched in here, these are 4-bit values which go into BCD to decimal decoder drivers, and they have 10 outputs, one for each of the
cathodes in the Nixies, and depending on the value on those 4 BCD lines, only one of those cathodes is grounded, which turns on the appropriate digit inside the Nixie, and so on for all 5 of them. Now, this gate pulse business has to come from an accurately known timing source, and that's provided by this 1 megahertz oscillator, which then goes through another set of decade counters, dividing by 10 each time. So we've got 100 kilohertz, 10 kilohertz, 1 kilohertz, 100 hertz, 10 hertz, 1 hertz. And the kilohertz megahertz switch on the front of the unit selects either 1 hertz for the gate pulse or 1 kilohertz, which gives a gate time for 1 hertz of 1 second, or 4 kilohertz gives a gate time of 1 millisecond. Looking at that in the circuit diagram, here's the input, which can go through the pre-scaler or directly to the input amplifier there. The output of that goes into the Schmitt trigger, and the output from that goes into the gating circuitry. If it's allowed out of the gating circuitry, it goes into the first of these decade counters, and there's a chain of 5 of them. When the count reaches 100,000, we have overflow, which goes here and drives the neon. At the end of the gate pulse, these latches are strobed to suck in those 4-bit values from the counters while they're reset and begin counting again. These latches hold the previous count while the counters are busy coming up with a new sample. The outputs of those go into the decoder drivers, 4 bits here, and then 10 cathodes drivers out there to turn on one of the digits inside each of the 5 Nixies. The time base, there's the 1 megahertz crystal, there's the oscillator, goes into these decade counters, so there's the timing chain for all the frequencies. The 1 hertz goes to the kilohertz megahertz switch along with the 1 kilohertz, and one of those 2 is selected to form the gating pulse. We can look at that in operation. So supposing we have it in kilohertz mode, pre-scaler off, and we feed in 12,345 hertz, right? 12.35 kilohertz. In 1 second, which we have because of the kilohertz setting, it will count to 12,345, and there we see it. And because this decimal point is on there, we can interpret that as saying 12.345 kilohertz. And sometimes, and this is true of all counters in all modes, the gate pulse may be slightly out of sync. There'll be a little bit of jitter in this timing relationship between the gate pulse and the incoming signal. So sometimes it will count 1 more pulse and sometimes 1 less. So that last digit is flickering. So sometimes we have 4 there, sometimes we have a 5. There's that same display again. If we now switch to megahertz, the gating pulse is only a millisecond, and in that time, at this frequency, it'll only be able to count up to 12 or 13, which is what we see there. Again, that last digit is flickering, and this photograph has caught it right between the 2. And because of the decimal point, we can interpret this as 0.012 or 0.013 megahertz, which is correct. That's what 12.345 kilohertz is. It's 0.012 megahertz. If we now increase the incoming frequency by a factor of 1,000 to 12.345 megahertz, but we leave the unit in the kilohertz position, still with no pre-scaling, we need 8 digits to hold that value, and we've only got 5. So it well and truly overflows, and the overflow indicator comes on, and we lose the 1, 2, and 3, but the 4 and 5 are still there. If we had 3 more digits, we'd see the 1, 2, 3, but the 4, 5 is there. To fix that, we switch to megahertz, so now the gating period is only 1/1000th of what it was before. At this frequency, we'll count up to 1, 2, 3, 4, 5, and again, we can interpret that as 12.345 megahertz. Still with that frequency, there's the same display in megahertz position, no pre-scaling. If we now switch the pre-scaler on, that input frequency is divided by 10, so it's 1.2345 megahertz, and in 1 millisecond, it'll only be able to count up to 1235. And the pre-scaler switch also moves the decimal point 1 position to the right, so we can again interpret that as megahertz, 12.35 megahertz. But now we've got an extra digit up front to allow for over 99 megahertz, and we can get up to, well, this unit will work to 200 megahertz, so we can presumably get 19999 if we wanted. If we still with that pre-scaler on, that same high input frequency, but if we switch it to kilohertz, because it's been divided by 10, we don't overflow by quite as much. We only lose the first 2 digits. The overflow still comes on, but we get the 345 at least, instead of just the 45. And to fix that, we do what we did on the previous picture, switch it to megahertz, and we get 12.35. I hope that all makes sense. Let's have a look at how the power supply works now. The mains comes in here through the on-off switch into the primary of the transformer, which has 2 secondary windings, a low voltage for all the logic, and a high voltage to run the Nixies. The low voltage goes through a full bridge rectifier to this circuit, which is a 5-volt regulator. It's got an adjustment, and out comes 5 volts, which runs all the logic, including the oscillator. All we need now is high voltage for the Nixies, and that comes from this winding, which goes through a bridge rectifier, and we get 210 volts to drive the Nixies. A bit curious the way they've routed this. It comes out here, down, along, up, across, up, back, up to the Nixies. Why didn't they just draw it up here, across, up to the Nixies? Bit curious. The thing I find interesting about this unit is when we want to run it from 12 volts DC, when we switch to the DC position, the primary is disconnected from the mains, so it's now floating, and the 12 volts DC is enabled into the circuit via this reverse protection diode and into the 5-volt regulator. So we get the 5 volts as we did before. The time base is running. The only thing missing is no high volts for the Nixies. And the way they've solved that is, you see how this 12 volts goes to the center tap of that winding? This secondary is now used as a primary. So if we are able to ground either side of this alternately, because the center tap is connected to 12 volts, if we can ground each of these alternately at 50 hertz, we'll be energizing the transformer just as before, and we'll get our 190 volts there, which gets rectified and filtered to 210 for the Nixies. And that's done by these 2 outside windings go through the diodes as before, and they're driven by these 2 transistors, which alternately ground one side of that secondary, which is now a primary. It has to be done at 50 hertz, and the way that happens is the 100 hertz tapping from the time base goes into a flip-flop. Remember, all this is still working because the 12 volts has provided DC to run the regulator, so all this stuff is running. The 100 hertz goes into a flip-flop, which divides it by 2, so we get 50 hertz out, but if we use the 2 outputs, the Q and the Q bar from the flip-flop, they are 50 hertz but exactly out of phase, just what we want to drive these 2 transistors. So that's how the DC operation works. I think it's quite cute the way they've repurposed that winding from a secondary to a primary, made use of the fact that they got 100 hertz sitting around to divide and drive these transistors. Very cute. Anyway, I think that's probably it for this guy, the Yaesu YC-355D frequency counter. Hope you found that interesting or enjoyable. Please give it a like if you did, and I'll catch you later.